Morgenstern, the instructor of record for Physics 1311. And if you're watching this video, then I'm already dead. No, not really, I just always wanted to say that. If you're watching this video, it's because OU is closing down due to the coronavirus, and so we will do the labs online. So the plan is, I will lecture to you like I would if you were in lab, then I will demonstrate how we will do the experiment, and then I'll provide you the handout, so if you can't read the board, that's okay. I'll provide you the handout with what's on the board and an Excel sheet with the data that I collected from the labs. So let's begin with Lab 7, the conservation of energy 1. So we have some new physics we'll talk about, starting with what is an isolated system and how energy behaves in it. So we can think of an isolated system as something that is just closed off with no interactions to the outside world. And then we have the two forms of energy, potential and kinetic. And so in an isolated system, if we add them up at any point, they'll equal a constant value. So how I consider conservation of energy, as I like to think of money, you have two people, each of them have $10. They go into a room, then one of them leaves and he has $15. The other person leaves and he doesn't have any money. The money went somewhere. Where's the money, Lebowski? There's $5 missing. So same thing here, just with energy instead of money. So we can break down our kinetic energy to K is going to be 1/2 mv squared, where m is the mass of the object and v squared is the velocity squared of our object. Then we have our potential energy, which has many forms, but in this lab we're just looking at gravitational potential energy, which we can write as U is mgh. M is the mass of the object, g is the gravity, gravitational constant, and h is the height. So to think about this, we could say that our potential energy at the floor is 0, and so here we have some potential energy, and if I drop it, it'll pick up kinetic until it hits the ground. So at the bottom, it has some speed v. Now if I hold it even higher, at like maybe twice h, it hits the ground a lot harder. It's going a lot faster because it had more potential energy. So that's what we're going to do here. This is our makeshift ruler. We're going to fire a metal sphere. And when we fire it, we'll fire it from the bottom of the ruler, which we'll call potential energy 0, so it'd be like the floor. And then it will have some kinetic energy, which we'll call K max, which will be its 1/2 m, then the v we fire at it squared. Then as the sphere rises and gets higher, it will slow down, so its kinetic energy will decrease and its potential energy will increase. Then at the top of the ruler, at the maximum height, it will stop moving, so v will be 0, so the kinetic energy will be 0, and the potential will be the maximum potential. So then we can look at some equations. Thinking about that, we know that the initial, since it's conserved, the initial energy, both kinetic and potential, will be equal to the final kinetic and potential energy. So in the beginning, the initial kinetic was max, potential was 0, and at the end, kinetic was 0, and the potential was max. Then we can write these out like from earlier. 1/2 mv naught squared will be mgh maximum. So we can see that the maximum height is going to depend on the initial velocity and the value of gravity. So we can use this. If we know v naught, we can predict the max height, or we can measure v naught and the max height and see if we have any discrepancies, and that's what we're going to do in this lab. The other thing to calculate v naught will be, we know the distance between the photo gates, and we'll measure the time it takes for the sphere to go between them. And this is what we did on the previous lab with projectile motion. We have this extra little piece here, 1/2 gt squared. Since we're firing the ball straight up, gravity's pulling it down. As it goes between the photo gates, it's going to slow down from gravity. So this little piece is to account for that slowing, so we have a more accurate v naught. So now the actual lab, I'll put the launcher straight up, and then I'll measure the time it takes for the projectile to go between the photo gates. I'll do this 5 times for each click, because it goes 1, 2, 3 clicks for the higher energies for 15 total trials. And then in part 2, you'll calculate the v naught from the time given for each trial, get the average, and then calculate the standard deviation of the mean for that v naught. In part 3 of the lab, you'll use the magic of math and physics to make predictions of how high the max height will be using the initial v naught you have, and then you'll calculate the standard deviation of the mean for the max height using this equation here, where this is just the v naught, g, and then the standard deviation of v naught. Then in part 5, we'll actually measure the distance of how high the object goes from the table, and we'll measure this little height we'll call H0, which will be the distance between the table and the first photo gate. And so we'll subtract this off the value we measure. And then we will align a ruler with the launcher and fire to measure how high the projectile goes. And I'll record this on a phone and step through frame by frame to get a more accurate measure of how high the max height is than I would by using my caveman eyeballs. So I will use 3 trials per click for this for a total of 9. And then on the report, you will just have to answer questions like normal. And I know you're all depressed because there's no graph on this lab. So let's go over here and look at the apparatus. This is the projectile launcher, the same one we used in the projectile motion lab. And so what we'll do is we'll take our Pasco box, turn it on. I want to put it on the time 2 gate setting. Then I'll push this down to 3 clicks. I'll go ahead and start this. Make sure I don't shoot myself. And then we got our time, and so I'll do that multiple times. And then after that, for the second part, do the same setup. Then I will put this here. I'll hold our ruler straight, and then I'll attempt to hold it straight. Then I'll launch it again, and you can see it's very hard to see with your eye how high it goes. So I'll do this multiple times and record it, and then get the average height. And then you'll be able to find on Canvas an Excel sheet with all the data, a handout like you would receive in lab, and a note sheet that says what's on the board. So thank you for your time and attention, and I will see you in Lab 8.